Okay, so welcome to the second installment of the Louisiana Coastal Neotectonics Workshop 3. So this is the sort of, we'll call it 3B. There'll be another talk tomorrow, tomorrow morning. So this will, so we can just start our, go to the next slide, Colleen. Okay, so the purpose of the panel here is to weigh the data, interpretations, and conclusions presented to them by regional scientists during 3 workshops in order to foster open discussion of the role of neotectonics in relative sea level rise and coastal restoration at the planning timescale. These workshops are meant to be a forum for the discussion of neotectonics and its potential impacts on management of coastal natural resources. So we're going to talk mainly about the planning timescale, although you can talk about subsidence and neotectonics on lots of longer timescales, but we're mainly concerned with the planning timescale. Our panel members are experts in areas of geology that are relevant to these discussions, such as sea level rise, subsidence, geohazards, stratigraphy, and delta building. Elizabeth Hayek from Pennsylvania State University is our panel chair. John Anderson from Rice University and David Morig from University of Texas at Austin are also part of our panel. Next slide. So the charge to our panel, sort of the basic questions we're asking them to think about as they listen to all the presentations that have been part of these workshops are, what are the risks, both temporally and spatially, to coastal Louisiana related to subsidence and neotectonics? Are the risks accounted for in existing 50-year coastal management plans? What is the likelihood, if any, of negative impacts due to projects by type? For example, marsh creation is fundamentally different than infrastructure projects. And what are the recommendations from the panel for future research and planning? Okay, so I'm now going to turn it over to Colleen McHugh from the Water Institute, who's just going to go over some ground rules and meeting agenda.
Great, thanks, Diana. I know a lot of folks joined us on the call yesterday as well, and or joined us in person for the first 2 workshops at UNO. But just to reintroduce myself, Colleen McHugh, I'm a planner with the Water Institute. And quickly to go over ground rules and tech check, just a reminder, if everyone could take a moment right now to make sure that you're remaining on mute. Please use the meeting chat window for asking any questions of the panelists or of the organizers. I think everyone is connected via the internet today, which is great. And as Diana mentioned, this meeting will be recorded and then we'll be posting it on YouTube and linking that to the Water Institute's website. So again, if you joined us yesterday, this is the second presentation of 3 that's part of this 3rd workshop, which we've broken into 3 days to give everyone a little more breathing room, given our virtual meeting platform. Yesterday we heard from Dr. Frank Tsai. Today we'll be hearing from Dr. Julie Bernier, and tomorrow morning, 8 a.m. to 10 a.m., we'll be hearing from Dr. Simone Fiaschi. And just a reminder, following the presentation, panel members will have time to ask questions of the presenter to discuss among themselves. We'll then reserve some time at the very end for answering questions that come in from the audience. And just another reminder, please use the chat box to ask any of those questions of the presenter. Reminder again about professional development hours, please reach out to Diana if you have any questions or materials needed for that. And now I'll go ahead and introduce our speaker for today. So we're excited to have Dr. Julie Bernier with us. She received her BS in Geology and Geophysics from the University of Wisconsin and her MS in Geology from the University of Utah. She has been a geologist with the U.S. Geological Survey since 2003. Her research interests include applying sedimentologic, stratigraphic, remote sensing, and geophysical techniques to better understand coastal and barrier system changes at historic to geologic timescales. The title of her presentation is Quantifying Wetland Loss, Trends, Processes, and Large-Scale Historical Accommodation Formation in Coastal Louisiana. So with that, I will go ahead and stop sharing our presentation and turn it over to you, Julie.
All right, thank you. Can everybody hear me okay?
Yep.
All right.
Yes.
All right, hopefully you can see my screen now, and it's the presentation view, not the presenter view, correct?
That seems to be correct.
All right. All right, so my presentation today is going to kind of review our methods, our data, and our results from the USGS Gulf Coast Subsidence project that was funded between 2000 and 2011 out of the St. Petersburg Coastal and Marine Science Center. All of our data reports and publications are available on the website shown here. And basically, before I begin, I'd like to acknowledge Bob Morton, who was the project PI, and John Barra, who did a large amount of the spatial analyses and trends analyses for us, in addition to the numerous other people who have helped on the project, whether it's in the office or in the field. The motivation for this project was to better understand the causes and trends of historical land loss rates in coastal Louisiana that resulted in the conversion of approximately 5,000 square kilometers of formerly emergent wetlands to open water since the 1930s. I'm sure that probably almost everybody on this call is familiar with the map shown here in some form or another. For this project, we conducted analyses at sites both in kind of the central delta plain shown here in the white box, and the western Chenier plain here. So the primary goals of the project were to better understand the physical processes and human activities that contribute to historical wetland loss, to more precisely constrain the temporal and spatial trends of that loss, and to quantify the three-dimensional or volumetric extent of wetland loss. We accomplished this by integrating diverse data sources, including satellite and aerial imagery, hydrocarbon production data, tide gauge and elevation data, as well as coring and topographic metric surveys that we conducted as part of the project. As seen on the plot shown here, early coastwide land loss data sets had pretty coarse temporal resolution, so pinpointing the exact timing of land loss was difficult. So one of the first things we did as part of this project was to add data points, at least at local study areas, using high resolution imagery and satellite data to refine the existing wetland loss curves and better constrain the timing of the greatest losses. And one of the things that the plot on the right shows is that using multiple images, there's a period of about 20 years or so where wetland loss rates were significantly higher than they have been recently. So from the satellite and aerial imagery, we observed similar timing and patterns of wetland loss across coastal Louisiana, irrespective of physiographic or geologic setting. And especially we observed that there was a rapid onset of wetland loss with peak wetland loss rates that occurred especially from the mid-1960s to the mid-1970s, although extensive losses and high rates of wetland loss persisted at some sites until the early 1990s. I'm going to show you a series of images that just kind of walks you through the timing of wetland loss at, in this case, 3 upper delta plain interdistributary sites in the Terrebonne Basin. At these sites, the extant emergent wetlands were underlain by thick aggradational peats that accumulated during the Holocene. And we can see that significant wetland losses were initiated by 1965. And we observed rapid submergence and conversion to, and near complete conversion to open water at these sites by 1974. Since 1990, we see some expansion, further expansion of the open water bodies, but not the extensive losses that occurred prior to this. I'm going to show the same, a similar series of images from Sabine National Wildlife Refuge in the western Chenier Plain. Here, the coastal wetlands formed between topographically higher beach ridges or cheniers along the Gulf of Mexico shoreline to the south and the Pleistocene uplands to the north of the study area. We see some variable timing of wetland loss across the refuge, with rapid submergence of formerly emergent wetlands in the eastern part of our study area between 1965 and 1978, compared with slower submergence of the wetlands in the western part of the study area, where the majority of wetland loss was actually occurred between 1978 and 1990. In the western Chenier Plain, we also see significant new water areas that formed between 2004 and 2008 following passages of Hurricanes Rita and Ike. And some recent unpublished work that John Barr and I have been collaborating on shows that a lot of these new water areas persisted or expanded between 2010 and 2016. So in addition to the similar temporal trends we observed at these diverse study sites, we observed expanses of what John termed wet marsh, which is essentially spectral signature and color infrared information where uniformly drowned marsh surface is visible in the color infrared and satellite and aerial imagery for some period of time prior to becoming completely submerged. And we interpreted this as an indicator that subsidence initiated wetland loss in these areas. Apparent variations in land and water areas through time can certainly result from variable water levels. However, one of the things we observed from basically the early 1980s to 2004 from satellite imagery was that the magnitude of these fluctuations decreased through time as extensive wet marsh became completely submerged and were no longer exposed under even low water conditions. We can use continuous long-term records based on changes in water level elevations at tide gauges as a proxy for subsidence. These records obviously include a regional or eustatic sea level rise component. The plot on the left here shows that there was a period of accelerated sea level rise right at the Grand Isle tide age from between the mid-1960s and the mid-1990s when compared with the record from the Pensacola tide gauge in Florida, which is located on at a relatively geologically stable location. We also looked at elevation changes at benchmarks, which are typically located along roadways and levees from repeat leveling surveys. And these measurements can provide subsidence rates that are averaged over discrete time periods. The plot shown here on the right is an example of data that was collected during 4 surveys along the Bayou Lafourche. And one thing that stands out is that there is close spatial correlation with some of the areas of the greatest subsidence rates, with increasing subsidence being down on the plot, and the projected superficial footprint of some of the large oil and gas fields in the area that are shown in gray on the plot. We also see that we also observed that there was a significant increase in subsidence rates between 1982 and 1983, shown in the green line, compared with subsidence rates measured prior to that. So when we look at production and land loss data from our upper Delta Plain study areas especially, we see close temporal correlation between oil and gas production volumes and wetland loss rates from the mid-1960s to the mid-1970s. As I mentioned in the previous slide, we saw accelerated subsidence rates into the mid-1990s. These accelerated subsidence rates may be associated with either continued productions of large volumes of produced formation water, even as oil and gas production declined, and/or it may be related to a lag between the initial production and sharp decreases in reservoir pore pressures and the ultimate irreversible inelastic compaction of the reservoirs and confining shales. We interpret this to mean that accelerated hydrocarbon production likely contributed significantly to and/or induced accelerated subsidence in these parts of the delta plain. We look a little bit more closely at some of the data. Although some early assessments concluded that the potential effects of production-induced subsidence in Louisiana were minimal and would be very localized, and instead attributed historical subsidence and wetland loss to the compaction of unconsolidated Holocene sediments. Modeled subsidence rates from the compaction of Holocene sediments by Meppel and others are only on the order of a few millimeters per year and do not and are consistent with the geologic rates derived from analysis of radiocarbon data, but are significantly lower than the observed historical subsidence rates. We look at some of the production data. It shows large drops in reservoir pressures of up to several thousand PSI that could have resulted in depressurization below expected hydrostatic pressure from stacked reservoirs at varying depths. And several studies modeled some of the effects of this production-induced reservoir compaction. Magnitudes of subsidence that were predicted from reservoir compaction by Malman and Zoback are consistent with observations of localized subsidence along over the fields shown here, again on that Bayou-Lafourche leveling line. Similarly, Chang and others, modeling by Chang and others, showed that in addition to the initial localized subsidence over the compacted reservoir, the observed pressure drops could result in time-dependent compaction of the surrounding shales that could exceed the compaction of the reservoir itself, and also had the potential to induce slip along deep-seated faults that could be propagated to the surface. A third study that modeled the time-dependent subsidence due to delayed reservoir compaction showed that subsidence on the order of up to a centimeter per year might persist for up to 30 years after the actual oil and gas reservoir depletion. So if accelerated hydrocarbon production induced the accelerated historical subsidence rates that were observed in coastal Louisiana, then we would expect that the highest subsidence rates are not likely to persist into the future. This is supported by the analysis of the inferred subsidence rates before 1965 and after, so before 1965 and after 1993 at the Grand Isle tide gauge, which are similar in magnitude to geologic rates predicted from the compaction of Holocene sediments. Kolkler and others reanalyzed much of the Louisiana production data and compared it to detrended tide gauge data from Grand Isle, Pensacola, and also Galveston, Texas tide gauges, and came to similar conclusions. So what does this mean for wetland resilience? That's a little bit less clear. Some recent papers suggest that the tide gauges may actually underestimate relative sea level rise and the contribution of, especially the contribution of shallow subsidence, and also analysis of geologic records and relative sea level rise rates reconstructed from basal peats indicates that there may be a threshold for marsh drowning in the Mississippi River Delta plain of approximately 3 millimeters per year, which has likely already been surpassed. To estimate the contribution of subsidence and erosion at historically formed open water bodies, we can use simple stratigraphic relationships where the one-dimensional or vertical accommodation that is formed is equal to the marsh surface elevation minus the water depth at an open water, a newly open water course site. In this instance, we see that the difference in marsh sediment thickness at the open water course site compared to with the emergent marsh is equal to the difference in peat thickness, and that subsidence can be estimated based on the elevation difference of correlated contacts. These magnitudes of subsidence and erosion are approximate because there may be imprecision introduced that could result from gradational facies changes and or sediment compaction during coring. And I should point out that in this simple model, the erosion term may include consolidation of peaty sediments through time due to water loss or oxidation. However, the method provides a minimum estimate of subsidence that has occurred at locations where historical pre-land loss elevations are not available, and we know that wetlands have been converted to open water. So from the results of our stratigraphic analyses showed that at the Mississippi River Delta Plain sites, the relative contribution to one-dimensional accommodation varied by both study area and physiographic setting. However, subsidence was generally greater than or equal to erosion, and erosion was always contained within the thick aggradational peat section, even where extant water depths are greater than the emergent peat thicknesses. And this in particular is a clear indicator that wetland loss at these sites was initiated by subsidence, because you cannot erode the uppermost sediments to the existing water depths and still preserve wetlands deposits. This is just an example stratigraphic cross-section from Ironton, our Ironton study site, which is located along a levee flank in the upper Delta Plain in Barataria Basin. At this site, the amount of erosion was approximately equal to the amount of subsidence at most core sites. However, you can see that the peat section, a significant amount of the peat section remains at most of the open water core sites. And at this location, we observed that water depths were significantly shallower than at other Delta Plain sites. However, the wetland loss, we attributed this to the fact that the wetland losses were also relatively young, with most of the losses occurring after 1978 compared with other upper Delta Plain sites. In comparison, at some sites in the upper Delta Plain and Terrebonne Basin, we observed that wetland losses were extremely rapid, with near complete conversion to open water within a period of about 10 years. And at these sites, subsidence accounted for almost all of the observed one-dimensional accommodation formation. Elsewhere in the Delta Plain, we observed differential subsidence on the order of about a meter on the west versus the east side of a pre-existing channel at Bayou Perot, and inferred that this was likely related to greater induced subsidence on the west side of Bayou Perot from deep hydrocarbon production at the nearby Delta Farms oil and gas field complex. In the lower Delta Plain, wetland loss rates were typically slower, and conversion from formerly emergent wetlands to open water often took on the order of 20 to 30 years, which suggests that slower subsidence rates may have been slower, and this in turn could have resulted in the greater observed erosion at these sites, as basically the subsiding marsh was exposed for longer periods of time to wave marsh edge or pond edge waves. If we move to the Western Chenier Plain study sites, the thin peat section at the Sabine National Refuge study areas was mostly or completely eroded at most of the open water core sites. However, all sites underwent some subsidence, and the magnitude of that subsidence could not be accounted for solely based on peat compaction. And the observed spatial variability in magnitudes of subsidence may be related to the proximity of the eastern part of the refuge, the eastern study areas, to the large hackberry oil and gas field that is located just north of the refuge. This is, again, is an example stratigraphic section from one of our Chenier Plain sites. And you can see that in the open water, most of that relatively thin peat section has been eroded. In the Western Chenier Plain, as at many of the lower Delta Plain sites, we observed areas of persistent wet marsh that remained visible on aerial and satellite imagery that is consistent with wetland loss resulting from subsidence until it was completely submerged. And we suggest that slower subsidence compared with the upper Delta Plain sites likely increase the vulnerability of the low elevation wetlands to marsh edge erosion and storms, such as in the Western Chenier Plain, hurricanes Audrey and Carla in 1957 and 1961. We also conducted single beam bathymetric surveys in the Delta Plain and GPS surveys at the Western Chenier Plain sites to provide more extensive spatial coverage and more accurate estimates of the average one-dimensional accommodation formation across the study areas. And these maps are just an example of single beam coverage at one site in the Delta Plain and GPS coverage from at the site in the Sabine National Wildlife Refuge. But you can see that the number of water depth measurements was greatly increased over the number of actual core locations here and here. So a comparison of wetland loss parameters derived from the coring and bathymetric surveys at the delta plane and Chenier plane study areas show that peat thicknesses and water depths, so peat thicknesses and water depths, as well as the magnitudes of subsidence and one-dimensional accommodation formation were greater at the delta plane study sites than in the western Chenier plain. We estimated historical three-dimensional or volumetric accommodation formation by multiplying the average one-dimensional accommodation at each study area by the two-dimensional area or extent of wetland loss that formed at the study site between 1956 and 2004. And we limited our end date to 2004 in part for consistency across the study areas as the project progressed, and also to avoid introducing complicating things with the effects of hurricanes Katrina and Rita especially. And what this plot shows again is that the largest accommodation volumes shown in the hatched things typically formed in the upper delta plane here, where both the magnitude of subsidence and the spatial extent of historic wetland losses were greatest. So again, just to kind of put some numerical values on that, if we consider the delta plane study areas and the western Chenier plain study areas as a whole, the magnitude of accommodation that formed just at our study areas in the delta plane was greater than 100 million cubic meters of accommodation between 1956 that resulted from wetland losses between 1956 and 2004. And in the western Chenier plain study areas, which do also represent a smaller footprint, we observed approximately 20 million cubic meters of accommodation formation during the same time period. Just to kind of reiterate some of our key findings, rapid onset and wetland loss across coastal Louisiana, we interpreted that this was likely initiated by subsidence, even at sites where erosion ultimately contributed as much or more to the total historical accommodation formation. And we interpret the close temporal and spatial correlation between wetland loss, subsidence, and hydrocarbon production to indicate that accelerated hydrocarbon production likely induced accelerated historical subsidence in many areas. The stratigraphic correlation of shallow cores presented here provides a simple method to estimate the relative importance of subsidence and erosion in converting former wetlands to open water. And this information can be used to inform management decisions at local sites. Additionally, accommodation volumes provide estimates of the new sediment that would be needed to restore wetlands to their pre-1956 extents and elevations. And just to kind of put the differences between, to put those numbers in perspective, in the western Chenier plain here, in the western part of the Sabine National Refuge, we calculated an estimated 8 million cubic meters of accommodation formation in this area that surrounded the former Greens Lake. Between 2004 and 2008, approximately 70,000 linear kilometers of vegetated earthen terraces were constructed in that area using approximately 0.7 million cubic meters of sediment that was dredged from the adjacent open water areas. And so basically the restoration sediment, volume of restoration sediment is an order of magnitude less than the total volume of accommodation that formed as the result of wetland losses. And one of the issues, especially in the western Chenier plain here, is that hydrologic alterations to the Sabine-Calcasieu Basin have channelized freshwater flow to the Gulf of Mexico, thereby significantly reducing overland flooding and fluvial sediment delivery to the interior wetlands. So most of these wetlands are highly sediment starved. And obviously in the Delta Plain, we see similar effects from the leveeing of the Mississippi River. Just to kind of some points to address some, not really knowledge gaps, but knowledge needs going forward. There's definitely a need for continued monitoring, both coast-wide and site-specific, of ongoing wetland loss using satellite and aerial imagery. just to be able to stay up to date with current trends and understand current trends in wetland losses. And we really need to continue to build a database of extant subsidence rates from interior wetland sites. Several studies recently have tried to tackle this, and they leverage the CRIM sites, including the sediment elevation tables and the benchmark data. And one thing that I've always thought would be a cool effort would be to try to combine these data with borehole compaction gauges at selected sites that could help to pinpoint the depth of the subsidence processes and the layers with which it's associated. This again is just kind of to put that need for interior wetlands, data from interior wetland sites into perspective. When we analyzed historical data, basically almost all of the data is derived from locations along roadways in urban areas or at levees or along levees. Whereas the CRIMS database consists of hundreds of sites at both degraded and relatively pristine wetland sites within the Delta Plain. And so this is just basically, again, emphasizing the need to continue to build and update a comprehensive coastwide subsidence database going forward. And with that, I'll take any questions.
Great, thanks, Julie. All right, we'll turn it over to the panel. David, can we start with you this time?
Sure.
Go the other way around.
Yeah. Thanks, Julie. That was great. I did have a couple of questions for you to help me understand sort of the uncertainty associated with these estimates. And the big one that I have is, you use 1956 as a baseline, right? Or you start with that. And so those must be aerial photographs that you're using. And
yeah,
is that like, what, is that just what, I have no problem with that, but I'm wondering how many aerial photographs you have. I mean, was that like just one flight through? So you had conditions at one time and that's it?
yes. So
that's true. How do you assess how representative that actually is?
With the early aerial photographs, and especially because they're also black and white, you do have to take them at face value in terms of water level conditions. Some of the early wetland loss trends relied on a 1974 National Wetlands Inventory data set that was based on imagery that was collected, for example, right after the 1973 Mississippi River flood, and has long been suspected to probably have show overages of wetland or open water areas because of that flooding.
Mm-hmm.
One of the things I've since learned is that I was really kind of lucky to start looking for historical data in Louisiana, because with all the oil and gas industry activities, Tobin flew surveys in the 1930s, the 1950s, the 1960s. The Corps of Engineers has additional surveys. And so there's a plethora of data. The information to really evaluate water levels is not available for that data, but you do at least have several data sets that were essentially collected at the same time in terms of within weeks or months of each other versus trying to piece data together from, several different years.
Okay.
When we started analyzing the satellite data more recently, you can look at water level variations,
right.
And we definitely saw water level effects associated with the passage of either winter fronts or hurricanes. And that was one of the reasons we looked at the total variation. And we really saw that basically between the 1980s and the 1990s, if you looked at the total water area, the water area variations ranged almost as by about 5 to 10%. And then after about 1993, the range of variation was only about 2 to 5% of the total water area. So that was one of those where we looked at it and said, well, we suspect that this means some of these areas have essentially become permanently submerged and are no longer ever emergent, regardless of water level conditions.
That makes sense. So when you do your, when you use the stratigraphy to sort of get us a sense of subsidence versus erosion.
Mm-hmm.
The stratigraphy looks, pretty layer cake. And of course, it's never quite as layer cake as you want. And you don't know what is missing. Can you just, I'm just asking, are you confident with that? I look at something like that right away and I'm suspicious, but I'm not the one doing it. I mean, if you say, yeah, actually we think that layer cake works, then I'll accept that.
So and I want to emphasize, we really focused on the really shallow stratigraphy, and basically
Right.
that uppermost peat section. We're not looking at basal peats. And there's definitely some of the early study areas, we primarily used vibrocoring, which can really affect the peat especially.
Mm-hmm.
And by the end of the project, we were using a combination of vibrocoring and peat augering.
Mm-hmm.
But most study sites, we tried to essentially crisscross with at least 2 perpendicular transects or more in terms of our coring transects. And by the time we had several marsh sites and several open water sites, it seemed, we felt pretty confident that we were not seeing large changes in either peat thicknesses or the depth of the contact across relatively small areas. Obviously, trying to correlate those between study areas, even like those 3 areas that I showed in the early figure where I had 3 study sites in the upper Delta Plain, even between those areas that are only separated by a few tens of kilometers, the peat ages and the thicknesses, you couldn't really correlate between study sites. So it's very much a local analysis.
Mm-hmm. Okay. All right, I'll stop right there and let others chat. Thank you.
Thanks, David. John?
We've lost him.
Sorry, I'd muted. I'll repeat myself. Thank you, Julie. That was very interesting. So my question has to do with the erosion that you refer to of the peats. Mm-hmm. And I'm curious as to what's actually doing the erosion. I'm sort of picturing this marsh that's going down and being filled with a freshwater body, which I would anticipate would be a very low energy system. So what is actually eroding the peat? That's question number 1. And question number 2 is, of that material that's being eroded, where is it going?
Where is it going is probably the harder question. And in the Delta Plain, there is enough kind of tidal exchange that some of that could be exported through tidal inlets. The erosion, I think, is primarily attributed to, even though these are relatively small bodies of water, the peat itself is so soft and easily erodible that even minimal waves over periods of years can begin to erode it. But we really didn't delve into the processes of the erosion so much as trying to really just tease out the magnitudes as far as the relative importance to forming that open water.
So it's really an assumption then, when you see 2 cores on the edge of the water body that have 2 meters of peat and cores in the middle of that water body that have 30 centimeters of peat, that 30 centimeters was originally 2 meters.
Yes, you have to assume that. In the Delta Plain, we saw evidence of that in the sense that, not one of the stratigraphic sections I didn't show, but at Madison Bay and Pointe de Chêne especially, at those study areas, we saw differences in peat thicknesses at the open water sites compared with the emergent marsh on the order of 10 to 15 centimeters. So essentially the whole inferred peat section appeared to have been preserved.
Okay. The other question I had, I don't know if you could flip back to that one, that I think it was next to your last slide that showed your stations. That's it. So when I look at those stations, I see there's one long transect that goes along the river levee. There's another in the middle there that I assume actually goes along a highway.
That's actually the old Bayou Lafourche levee. Yep.
Oh, okay. And so these are all, except for that one bit of the central transect, these are all sort of shore perpendicular transects.
Yes.
Which is not the ideal transect if you're trying to get a handle on subsidence.
Yes.
So what strikes me is that I'm hearing something very different between your presentation and Tor Tornquist's presentation. And on the one hand, we're hearing that, well, it's really oil and gas production that has caused a lot of the subsidence, whereas Tor is saying it's really subsidence that's causing a lot of the, it's probably a combination of both. And the reality is, if Tornquist et al. 2020 are correct, and it's only about 3 millimeters accretion rate, that's sort of the critical threshold for subsidence for marsh removal, erosion, it probably doesn't matter. Because I think in either case, we're going to have subsidence, with the exception of maybe tectonic subsidence, but certainly oil and gas extraction or Holocene compaction both seem to exceed that 3 millimeter threshold.
Right.
But I just would question whether you think your data points here are really suitable for actually saying, well, it's oil and gas extraction and not subsidence, given the nature of these shore perpendicular transects. I really question whether those transects are going to show us, because to really get at that, what you would want to do would be to have transects that might cross a river valley where the Holocene sediments might go from 50 meters thick to 5 meters thick, which is probably a pretty realistic number. And then if you did the calculations on substance, that would be a quite significant difference. And in fact, Tornquist is arguing that they see those kinds of differences. So I'm still a little bit, I guess, uncertain about the oil and gas. I mean, I realize oil and gas extraction can be a significant factor here. But when we're trying to really get down to nuts and bolts of saying, well, on a regional scale, what areas are being most impacted by oil and gas extraction, which may have discontinued in one area or another, and what areas are being most impacted by subsidence. Because I think that's something our panel would like to be able to do, is to try to separate out those two.
Right. So I think, I mean, with the historical data, of course, we have to work with what was already there, which are these, the along levee data sets that were surveyed by the National Geological Survey. And I think one of the big things to consider is that these historical data sets really are giving very, very short-term subsidence rates compared with geologic processes. And it's that very short-term acceleration of rates that we saw both in the tide gauge data, which is also not in an interior wetland, but sites in the interior wetlands only have approximately, most sites only have a 15 to 20 year record. And the long-term data is to show that historic acceleration and then apparent deceleration of data over timescales that are of the same magnitude of the oil and gas production. So that's not to say that the deeper subsidence is not going on at all. It's just that really rapid wetland loss and those really rapid short-term periods of subsidence appear to have been induced by something other than geologic subsidence.
Yeah, I don't think any of us disagree on that tectonic subsidence is minuscule here and probably not an important factor. But you've presented some very compelling evidence that at times when there was significant oil and gas production there was accelerated subsidence. I don't think anybody questions that. TOR has presented some compelling evidence to show that sort of spatially, areas of high subsidence correspond to areas of thick Holocene sections.
Right.
So I'm just trying to get at, obviously both are important, and I'm trying to get at, whether or not it might be possible to sort of separate those two out, because they're obviously both important. I don't think we're denying that, but you seem to be, I get the impression you're not a big fan of compaction. But
it's just the modeling results seem to suggest that the geologic compaction of the peat section cannot approach the observed magnitudes of subsidence. It can contribute to it, but it does not approach across some of these areas where we're observing a meter of subsidence in a very short period of time, because it had to have occurred between the 1950s, when the marshes were essentially continuous, and 1990.
I totally agree. Don't think we're doubting that at all. I think we're just trying to understand if subsidence due to compaction over decadal time scales of 50 to 100 years is not, I think, based on what TOR has told us, is still an important factor. And there certainly seem to be some areas where it may be the dominant control, but I think the two probably are both operating, and it looks as though fluid extraction is resulting in substance that's operating at a high, as you point out, at a higher frequency. The response is faster when you start extracting fluids out of the ground.
Right. Compaction
seems to be pretty linear depending on the thickness of the sediments. So you could almost come up with an equation in which time, the timing of compaction, or rather substance, thickness of the Holocene, etc., could all be entered into this equation to tell what's been the cause, but more importantly, how might you, if it's compaction of sediments, there's not much of a way to shut it down.
Right.
If it's fluid withdrawal, at least you can point the finger and say, this is a result of fluid extraction in this field or in this area.
Right.
So ultimately, it seems we want to be able to get there if we're going to solve the problem, or at least say the problem can't be solved in this area. We just have a lot of compaction that's going down fast. It's already exceeded the 3 millimeters per year, and there's not much we can do about it other than add these volumes of sediment.
Right.
So, well, thank you. That was very helpful. And I'll turn it over to Liz now.
All right, thanks a lot, Julie. That was really cool to see everything. I guess, let's see. So David and John picked up a lot of good questions. I guess, one remaining question I have for you is just based on what you've seen. I guess I'm still just trying to get a sense on. I didn't quite pick up on exactly the sort of reasons why erosion versus subsidence, why the difference in the dominant effects in different areas. And so I guess, like, from what you've seen, how predictable is it where to be able to look at an area, or what would you need to look at an area and predict whether or not the sort of background subsidence would be dominating versus the erosion effects would be dominating?
That's a difficult question. We certainly never got to the point where we could have confidently looked at something and said, it's going to happen here. We looked at a lot of oil and gas data. One of the things in the Delta Plain is you have many more, and generally, with a couple of exceptions, much larger oil and gas fields than you do out on the Chenier Plain. So you potentially have combined effects from multiple producing fields versus, like in Sabine, I think there is some pretty clear evidence in terms of the fact that subsidence seems to be significantly greater in that area. It does not approach the magnitudes we saw in the Delta Plain, but at the study area immediately south of Hackberry, that is some at least some highly suggestive evidence that there is additional subsidence there caused by the proximity to that oil and gas field.
So at least locally where you see higher subsidence, it's proximity to the oil and gas fields. Okay.
And again, with the existing historical data, it's really difficult to try to correlate those subsidence rates along those levees into the interior marshes and say, do I see a trend here? Is this or is it not? And I know Bob tried that for many years and sometimes convinced himself he saw a trend and sometimes convinced himself that he didn't see a kind of an alongshore trend. So.
No, that makes sense. That's yeah. Good. Thanks. I think actually that's it for me. So that's good.
Can I ask one more question? If Liz
Sure.
is.
Mm-hmm.
Yeah, well, we have this map up here, the CRMS map. So, when I look at the yellow dots, they seem to start right at, as I recall, I'm not an expert on Louisiana geology, Dave can pipe in on this, but that looks to me to be about the Pleistocene-Holocene contact, where you go up onto these old Pleistocene terraces, and south of that, you're dealing with thicker Holocene sections. So I'm wondering why there aren't many yellow dots north of that contact, where we might expect to see minimal subsidence due to compaction of Holocene sediments, because there are very few very thin Holocene sediments, but still see high rates of subsidence due to gas and oil extraction or fluid extraction.
I'm sure there's somebody on the call who can correct me if I get this wrong, but I'm pretty sure that all of the CRIMS locations were selected based on the Louisiana coastal zone boundary that was defined many, many, many years ago, and really was really constrained to those wetland areas.
Yeah, and there's a reason why the area, the point I guess I'm trying to make is that in the area where there are no yellow dots, they avoided those areas because they didn't view that as having serious issues.
Right.
But to the south of there is where the Holocene thickens up, and best information I've seen is pretty abruptly. That's out on if you go to the west, that's the Louisiana Cheniers, and we have quite thick Holocene there. So,
right. So John, I'll just say, so all the yellow dots represent CRIM stations. Is there anyone from CPRA who would like to comment on this question? Krista?
Yeah, so, hey, so just to clarify, so the yellow dots are CRIM stations, and so as Julie was mentioning, those sites were determined because they were in these areas with wetland sites that were able to go ahead and establish the SET stations and the sort of water monitoring and all those different things at these wetland sites. And so they are restricted to the coastal zone that CPRA is sort of concerned about with our mandate. And then also to, I think that the point to be made that these are all sites that needed to be selected to be able to collect all that wetland data. So if you're going into any of these sites that are outside those particular areas, we have other monitoring programs within CPRA. So we have the SWAMP program that collects data outside of these wetland sites necessarily. And there are other sort of complementary monitoring programs that are in place. But in terms of CRIM sites, those wouldn't be located in any of those areas that are in the more upland areas or in the Pleistocene Channel Valley or anything like that. So.
Thanks, Krista.
Can I ask another question? So two things. One is, that's really interesting that there's a whole nother set of data out there, these swamp sites, which I hadn't heard about before, but we have mentioned in other meetings how as unique as the CRIMS data set is, and it's a remarkable data set, it is just one part of the elephant, right? And so there's no doubt that we would have a better understanding of what's going on if there were similar kinds of data from the swamps or from something that didn't have, that was to the north of those.
Yeah, so as Carol had mentioned yesterday, there are other initiatives to collect other subsidence data, and that particular data through the lowermost program. The SWAMP program in and of itself is just sort of it's an umbrella program that kind of brings in sort of these ancillary data sets that aren't the CRIMS data, and it isn't, necessarily there isn't like a broad subsidence data collection effort or anything like that in those other areas. It's other data that's being collected around the margins. So I would say that in terms of what CPRA is collecting on subsidence related data, so there's sort of internal studies that have been mentioned in other presentations, looking at reanalyzing GPS data and sort of that information that's coming out of like Mark Burns et al. and his work. But there isn't like some secret treasure trove of additional data that is out there.
Okay, just
we're not keeping anything from you, Dave, I promise.
Yeah, no, I'm not, yeah, I'm certainly not accusing anyone of that.
No.
It would be great. I'm just, more, please, always more. I had a question for Julie though, about, since you've done all this, looking at these time-lapse images and showing, the growth of this open water, while you were doing that, did you also monitor sort of what was happening with the widening of all the canals and the development of the canals? Do they figure into this analysis at all? Because I'm always interested they're certainly partitioning the ecosystem, right? And even some would argue they play a big role in land loss. So I wonder if you have anything to say about that.
So one of our study sites at Bayou Perot was actually, it crossed a pre-existing canal, a tidal canal. At Bayou Perot, it has significantly expanded during the time frame covered by this project. That was where we saw differential subsidence on the eastern and western side of the canal itself. We did not look specifically at like newly dredged canals. And in part because a lot of people, like a lot of Shea Penland and folks had done a lot of looking at that prior to the project initiating. But yes, we definitely did pick Bayou Perot in part because it was not a formally continuous wetland, but was an existing channel. And we definitely saw more erosion there, but we also saw significant, as much subsidence there as we did at some of the other studies areas, at least on the west side of the channel.
Okay, thanks.
And I would encourage you to go to the website because for every one of the study areas, I have maps like the ones I showed, where for each of the study areas where it shows the progression and the timing of the wetland loss and all of the coring and example cores and cross sections and whatnot.
I have a question, if I can, and this is for Julie. Julie, I'm trying to still with this same figure showing data points, match things up here. And so in particular, I'm trying to figure out where these transects are that you have. But what I would refer to is, correctly, I think it's correct, the Red River alluvial valley is this sort of triangular shaped area yeah, you just went up the one side of it, the eastern side, and then you can go down the western side and you see it's a delta, it's shaped like a delta, right? With a sort of a distributary system in there, except it's actually a seaward converging drainage system, suggesting it's a older system that was incised as sea level fell, unlike a delta distributary system. So that sort of tells us that's an old system. And I think we know that's the old Red River, Pleistocene Red River Delta alluvial plain. So we would not expect to see any subsidence due to compaction anywhere within that area, since there's no Holocene.
Right.
There you go. But we would expect to see, some areas, perhaps areas of significant subsidence due to fluid extraction in that area. And is that the case? Do we see that in that old Pleistocene province that there is still areas of significant subsidence?
I honestly do not know. We did not collect any data, or we did not analyze any data from up in that area. I mean, I think you could spend years trying to collect data across the entire coastal plain, and even more years trying to add data from the uplands. One of the issues actually that we often ran into when we looked at expanding west was there's a lot more private land ownership and micromanaged areas in the Chenier Plain that were an issue for just getting access for field work and whatnot. We had more access, and we also had more contacts in the Delta Plain that Bob had created and it had over the years, and we were able to get onto some private land in the Delta Plain, but most of our study sites did need to be located on public lands to get access. And I think part of it too, when Bob he had begun the work and had extensive data in the Delta Plain, and really wanted to kind of jump all the way to kind of the opposite conditions in terms of Holocene thickness, et cetera, in terms of moving all the way out to the Western Chenier Plain.
Do you know, in your study area, the Western Chenier Plain, the thickness of the Holocene there? I mean, I didn't see a map that actually showed that area on a larger scale map, so that I could get a sense of where that study area lies relative to the Sabine and Tsai Valley, for example.
So
these inside,
yeah, the refuge itself is basically occupies the whole swath between the Sabine and Calcasieu rivers.
Okay. And so there's at least two large incised valleys there, the Calcasieu Valley and the Sabine Valley, neither one of which actually sit under the current Sabine Lake or Calcasieu Lake. And so those lakes aren't any longer sort of sitting over the old valley. So it would be very interesting to know how those subsidence rates relate to those incised valleys.
Right.
Because if there's no correlation, then that seems to dispel to some degree the compaction issue.
Right.
Because once you get into that part of the world, all the way down into Texas, we just don't see a heck of a lot of subsidence until we get into an incised valley where we have 50 meters of Holocene. But as soon as we come out of these valleys, we're up on the Pleistocene.
Right.
And that's pretty well what we're seeing in the Sabine area. We're seeing a large area where there's no Pleistocene, or where there's hardly any Holocene. And then you drop down into these two valleys that have been mapped. They were mapped by the USGS originally, at least the Sabine was. So it'd be very interesting to plot some of those data on top of those incised valleys to see how they correlate.
Right. Yeah, no, we definitely did not do that at that location.
I can tell you for a fact in Texas that they correlate beautifully. And that you've either got Pleistocene within a meter of the surface along most of the coast. But when you drop off into these valleys, so you look at the Pier 21 tide gauge record, which everybody likes to cite, but it happens to be sitting right in the middle of the Trinity incised valley.
Right.
So you can't take that subsidence rate, as some people have done, and apply it to Galveston Island or some other area, because that's not the rate of relative sea level rise anywhere else. It's not even a good rate for the upper part of Galveston Bay. So it's very important, I think, to plot these data on top of these maps, that existing maps that show where these thick Holocene sections are.
Right.
Hi, everyone. This is Carol with CPRA. I just wanted to interject something real quick, related but not 100% on topic. CPRA produced in December of last year a Calcasieu-Sabine Basin report. So CPRA's Lafayette Regional Office was involved in putting this report together, and Tommy McGinnis and Leanne Sharp, both who look at CRIMS data regularly for subsidence type impacts and look at the RSET data quite frequently. So I sent that report to the Water Institute to send to you guys. And the main reason I wanted to bring it up is there is good discussion about the Chenier Plain and the data that we've collected there over multiple years. And there's a good bit of discussion about erosion. So Julie was absolutely right. The erosion versus subsidence topic, and figuring out what to attribute what to is an extremely difficult topic. But I just wanted to make sure that everyone knew about that Basin report, which I think probably has some information that y'all would be interested in.
Yeah, thanks, Carol.
Great. Thanks, Carol. Thank you, panel. I think I'll jump over to the audience questions now. I think this one from Maricela at the top has been largely addressed. There's a question from Honora Buris. Do you account for plant death in the fresh marshes due to saltwater intrusion or produced water, which could be a major factor in increased erosion and/or loss of peat?
No, we did not really look at any of the biological processes. Neither Bob nor myself have any background in that.
Okay, thanks, Julie. And then I'll just point out for our for Julie and for our panelists that there's a number of comments here as well for us to kind of look at from folks. All right, we just got a question from Elizabeth McDade. Why is the process of development of accommodation space formed by faults during deposition, growth faulting being ignored? And she has some follow-up notes. I don't know, Julie, if you can read this full question chat.
Pull it up. So let's see here. So I think partly it goes back to time scale. Bob did some studies. He with Harry Twitchell, they tried to map some of the growth faults to see if they came up to the surface, especially at areas where, when you looked at the wetland loss maps, there seemed to be very linear, in at least initial formations, and they were unable to, in any of the places they looked, really see any conclusive evidence of the deep faults that had propagated to the surface in those areas. And I think that they looked at that data. The other thing was whether or not growth faulting that operate again at geologics timescales could have actually induced the observed wetland losses and the observed rates of subsidence at these really short historical timescales. So I think the growth faults probably contribute more to the long-term geologic subsidence. That is certainly a component, but was not necessarily a dominant component of the real short-term loss.
Thanks, Julie. I am seeing a follow-up from Maricela. could I actually ask you, Maricela, maybe to go off mute and ask your question directly to make sure we've got that clearly captured?
Sure. Hi, everybody. So I have two questions. One is, what's Julie's and the audience opinion on the accuracy of the analysis, the modeling that has been done so far to support the role of compaction and subsidence due to hydrocarbon production? That's number one. And number two, and Julie was talking about that, the role of fault, natural like growth fault movement in an episodic fashion, which is somehow supported by earthquake activity in Louisiana.
So as far as essentially the subsidence versus erosion estimates, those definitely have some error associated with them, and you want to emphasize that it really is a relative magnitude. When the actual vertical accommodation you measure by looking at marsh surface elevation to water depth is a hard and fast number, but there definitely can be imprecision in the actual subsidence and erosion estimates that result from facies changes, both laterally and vertically, that result from compaction. But when what we were really looking at was the fact that when you consistently saw that the amount of subsidence, for example, greatly exceeded erosion at some areas, or areas where they were approximately equal. So we were looking at the relative contributions of the two, and those values definitely have some error associated with them that is difficult to fully account for based on the actual, just the small number of cores. However, when we did have vibrocores and we basically collected a compacted peat section, we did take measurements that account for that compaction and tried to linearly decompact the cores, which is not perfect, but it does try to account for the compaction of those soft sediments during coring.
Yeah, I was talking more about the analysis done like by Malman and Zobak, by Chan and Zobak. I haven't seen the Chang paper, but it from what you have described, it looks that the role of shale dewatering can play a role. And then the contribution of this compaction reservoir or hydrocarbon reservoir compaction on fault reactivation.
Right. I can find the link to the papers and send them to you. That the fluid-induced subsidence and whatnot, the modeling is well beyond my area of expertise. I'm principally stratigraphy and sedimentology. But I can go find the actual DOI link to the papers and post them on the chat page.
Yeah, Maricela, this is Mike Miner from the Water Institute. In earlier workshops, we had presentations discussing like episodic earthquake movement maybe, and we could send the relative references to that, and also the Chan papers. We can post those.
Yeah, thank you. Thank you very much.
Yeah, great. All right, well, I think with that, we might close the full presentation for today. Thank you again to Dr. Julie Bernier for a great presentation, to the panel, again, for a thoughtful conversation, to everyone in the audience who has joined us today, who has joined us for a number of these in the series. Reminder that we will be convening again at 8 a.m. Central Time sharp tomorrow morning to hear from Dr. Simone Fiaschi. So hopefully folks will be able to join us again tomorrow morning. Diana or Mike or Krista or Carol, any other kind of comments before we close?
No, I just wanted to thank Julie for the presentation. We really appreciate it. And it's very important and very important work to CPRA.
Thanks, Julie.
Yeah, thank you, Julie, and thank
Yeah.
you, panel.
Thank you.
Yeah. Thank you, Julie.
Thank you, Julie.
And yes, the presentation is recorded. And we'll be sending that out.
So we're done?
AM tomorrow morning.
Yep.
Okay. Bye.
See you in the morning.
Thank you, everybody. Bye. Thanks, everyone.